Good evening on the discussion of biomass conversion and biorefinery course. Am I audible? Hope so. I'm audible only. I am speaking a little bit slowly as I'm. Thank you. So my voice is not good, and the other thing is I'm in Australia. Everyone is sleeping here. It's night time over here. So I'm sharing. I want to tell you, if you are waiting for the thing that I asked, because last in the last lecture some student asked that what is the pattern of the exam. I asked to the professor in the mail, as I also not personally contact with him, but I didn't get any reply from him. So maybe you can also ask. I don't know. I'm sharing my screen now. Okay. Okay. Thank you. Hope so you can see my screen. Uh, Today we'll discuss about the week 11 discussion, and the basically the assignment problem solution from the week 11, and from the week 12 we'll discuss the topic of which is integrated biorefinery, which is the last lecture for this biomass conversion biorefinery course. We'll go through the important aspects of this chapter, and in the next chapter will be now next lecture will be the last lecture for this course from my side, and in that lecture we will solve the assignment and we'll summarize the whole course. Once again we'll go through the all important topics of the whole course, and that's how we can complete this course. So the lecture notes involved on these two chapters are from 30 not lecture note 31 to 37. uh, he is our professor Kostuba Mohanty. He is a facilitator of this course. I want to give my introduction. I am Bhavik Mahant. I am a PhD student in the IIT Madras, and these are my mail ID and mobile number. You can note it down if you want to have any doubt regarding this course. I am again telling you, we are not responsible for anything related to course like exam, and as well as the uh, what are the assignment solutions are right and wrong, because there are a separate team of TA maybe who is working with the professor to setting it up. We are the additional TA, and we are also, you can see, we are from different IIT. So we are just going the problem solving session, or just discussion of this subject in every week. That is our duty. I along with Arihant, he is a second another TA. He is from IIT Roorkee, I guess. Okay, so I will add some details, but more major detail we already discussed in the last lecture, so we'll not go through again and again. But if you talk about the week 11, then it is a title is organic commodity chemicals from biomass. So there are we have gone through the whole 10 chapters before that, and we have seen that many different kind of organic chemical, as well as many different kind of let's say gases like hydrogen, methane, as well as in the same type we can also produce um, agriculture fertilizer and many products from the biomass. But we majorly cover the ethanol and more in much more detail, but there is a separate class of chemicals which are commodity chemicals are the chemicals which are directly used in the commodity as a commodity, or in the daily life of the users or customers, or they are using as a intermediate product to form the another produce another set of chemicals. So if you think about the biomass, then there are many ways you can get this kind of chemicals. So biological derived chemicals, which are basically alcohol and acids, which are you will get from the acidogenics and from the glucose and hemicellulose. If you are processing it, then you can get this kind of chemicals. If you integrate the same processes with the biological derived, means biologically derived means you will use the microorganisms or enzymes in order to derive this. If you integrate with the catalysis, you will get isoprene, fatty acid, lactic acid, and polyhydroxy alkanoate, these kind of chemicals. These are a much more advanced chemical than this, and in the sense of structure and complexity, they will be have the specific applications. And there are the chemically derived chemicals which are basically reacted from the we can go the chemical reaction on the biomass, and you will get majorly acid and alcohol from this. Some of the importance are fulfiller, glycerol, xylitol, sorbitol, and glutamic acid. And then they will be again converted into the many other chemicals, like if you talk about fulfiller, then it is converted into the THF and all. THF is the tetrahydrofuran, which is all this information is there in this whole chapter. There's professor also discuss about this thing. But some chemicals are basically both biological and chemical derived, means they require some uh, enzymes, microorganism kind of biological medium. At the same time, there are some chemical reactions also going on. So 3-hydroxypropanic acid, succinic acid, aspartic acid, isobutanol, all are important chemicals. Now we don't want to waste much more time because it's already discussed. So there are questions asked from the, basically we discussed this, that there are different kind of synthesis processes are there. So major synthesis process is the thermochemical synthesis for this commodity chemical. So if you can see that most of the organic chemical additive commodities like synthesis gas, light olefin, ethylene, propylene, butadiene, and BTX. BTX means benzene, toluene, and xylene. And the different kind of chemical structures are developed by using the thermochemical process. So with the exception of synthesis gas, each of these building blocks is hydrocarbon. So if you just not talk about the synthesis gas, which is CO plus hydrogen, but other than so all are the organic compounds. And in biomass, polysaccharides are there, which are long chains of saccharides, I mean sugars. Wait a minute, I just want to see that I start recording. Okay. So they are basically sugars, long chain of sugars, and they are converted into the many hydrocarbon chemicals. And then depolymerization carbon oxygen bond cis-1 are therefore necessary on the large molecules. So cis means you have to cut the long polymers into a short, and then you have to synthesize symbolic building blocks. The question asked in the assignments that the building blocks of synthesis of chemical, commodity organic chemicals, synthesis gas, light olefin, ethylene, propylene, and butadiene, and BTX can be obtained from the biomass feedstocks by that's gas conversion. So as it is in the first line itself, it is a thermochemical process, which are this is the route which is used for this conversion. So we can see answer is the thermochemical conversion. So this is the answer. Now there are some important explanation which we did last slide. In this chapter, most of the part I added from the professor itself, because these all are the information and you need to understand the information. There are some questions asked based on that information. So biomass feedstock explains several opportunity for varying product distribution as a function of market demand and other factors which optimal mix of product is chosen based on feedstock characteristics. So according to your feedstocks, according to your the biomass, uh, there are various kind of product you can produce from the different kind of biomass, but you need to see that which product has the market demand, and which are required for the which have more than one or two applications and utilization, then you can go for these kind of chemicals. So predominantly if you see the xylose and mannose are the mild acid hydrolysis. If you do the hemicellulose, then you will get the xylose and mannose, which are typically 5 and 6 uh, carbon sugar. So now acetate of this SO yields a glucose solution which can be combined with mannose for alcoholic fermentation and lignin residue. If the so this is you can do with the alcoholic fermentation lignin residue. This is one of the example. If you want to produce furfurar, this is actual name is 2-furan carboxyaldehyde. It can be made from the xylose. So mainly this kind of commodity chemical can form from the C5 and C6 sugars and lignin systems. So other compounds that can be produced directly from the biomass in good light, but we do not retain the basic structural characteristics of biomass are classified as a commodity chemicals. So examples are many as in the beginning of the class, as Professor told. Okay, so that is some information we not go to and discuss again and again. This is chemicals from the biomass. If we talk about the C5 sugar, then you will get the furfurar and xylitol as a important chemical. We talk about the C6 sugar, which is mainly available in the if you for the cellulose, then you will get lots of glucose. So this convert into glucose, then you will get this kind of aldehyde acid as well as alcohol out of it. So for an example, ethanol acid, aldehyde, acetic acid, acetone, glycerol, butanol, citric acid, lactic acid, and many more. And applications are like they can be used in antibiotics and vitamins. And the same sugar you will get glycerol sorbitol with the different metal and hydroxymethyl, and then the if you can convert the separate these sugars into the fructose also. Fructose may be used as the artificial sweetener. We talk about the cellulose, then there are many derivatives of cellulose acid, esters, nitrates, ether, and xanthans. While lignins, from the lignins you will get the phenol, vanillin, lignin sulfonates, and some other uh, extra compound of the biomass. If you use, then you will get halogenates, alcohol, kata, saponin, sterols, and many more. So basically, if you this was the example how the produce the different kind of chemicals, commodity chemicals as well as synthesis gas. So first you have a biomass, you will do in the presence of oxygen and steam, you convert it into the gasifier, you put it into the gasifier, you get the synthesis gases and bunch of the chemical. If you separate the synthesis gas, then you get hydrogen, methanol, SNG. SNG is the synthetic natural gas, ammonia, oxo alcohols, and hydrocarbons. So hydrocarbons, both alkane as well as alkene you will get. So this is how this kind of chemical is the basic route of production. Now there are some questions in this we discuss about the pentose commodity chemicals which has the 5 sugar um, ch- uh, structure, and then hexose chemicals and lignin chemicals, lipid chemicals. They separate different kind of biomass product. If you take it intermediate from biomass, you take it and you have which kind of chemicals you will get. But there are some questions asked from this kind of derivation of the chemicals, so that's why I cover again. So pentose chemical is the foremost example is the xylitol, which is a pentahydric alcohol. It's alcohol only, and it is manufactured by hydrogenation of the aldehyde group in the xylose. Now, if you see about the question asked in the assignments, then the one of the question asked is the one of the unique reactions of the dash known since the 19th century is cyclodehydration to yield furfurar. So in that same uh, discussion, it is mentioned that the one of the unique the reaction for this pentose chemical is which is famous since well known since the 19th century, which is a cyclodehydration to yield furfurar. So that's why this is a pentose derived chemical reactions. So answer is pentosis. Now xylose, for example, is dehydrated by acid treatment to one or two intermediates to form furan substituted aldehyde in quantitative yield of the xylose. So means you can convert it into the furan, and this furan will be ultimately converted into the fulfuran, or yeah, the fulfuran structure has the furan molecule. Furan is basically five. Here one oxygen is there, and it's this kind of structure. Okay, then the another question asked is the two principal furans from which many derivatives are available are tetrahydrofuran and tetrahydrosulfuryl alcohol, both of which are manufactured from which. So again, the question was the answer was given in the this line, which is the furfura. So the two principal furans from which many derivatives are available are the tetrahydrofuran and the tetrahydrofuryl alcohol, both of which are manufactured from furfura. And for manufacturing for Ferrari, you can use this pentose derived chemicals like this cyclodehydration, and you will get this furfurar. So answer is furfurar is the mother mother compound from which you will get the tetrahydrofuran and as well as the tetrahydrofuryl alcohol. And that two these two is much more famous, and they will have many kind of derivatives after this. So furfura is converted by the catalytic. Now how it is converted into furan? There are many kind of different chemical reactions you will go. If you go for the decarbonylation from the catalytic medium in the form in the presence of catalyst, you will get the furan. You go for the catalytic hydrogenation, mean the addition of hydrogen, then of the aldehyde group, you can get the fulfilled alcohol. So CHO is there. If you add sorry, it's CHO is there, you can convert into the CH2OH and then it will go for the tetrahydrosulfur alcohol. Furan is converted into tetrahydrofuran by catalytic hydrogenation and there goes a large number of substitution addition reaction. So many things will be removed and many things will be added. Now I just want to see one is there. Okay, now hexose derived commodity chemicals. So there are questions asked from the hexose also. So basically hexose are basically sugars, sugar syrups, because cellulose, if you go into the glucose and fructose, those all are the six hexose means six carbon chain. Yeah, someone is there. Yeah, yeah, ma'am. Actually, we are discussing with this 11 chapter 11 assignment problems, and I'm drop as you asked the questions regarding that pattern of the exam. I dropped a mail, but I didn't get any reply from the professor till now. Okay, this is was just for information. So in the hexose there are commodity chemicals. Basically they are the sugars which has six carbon chain chemicals or six carbon structures. They are converted into the commodity chemicals, and these are known as the disaccharide cellulose. So glucose 3 glucosides, which is synthesized not from the glucose but by careful hydrolysis of cellulose. So three glucosides and a different kind of chemical which are actually a commodity chemicals. Glucose is converted into gluconic acid, which we saw in the first slide itself. It is also chemical which is commoditized, and oxidation of the aldehyde group to the carboxylic group. So if you oxidize aldehyde, then it will go into the acid. If you reduce aldehyde group, then it will go to the alcohol. So and due to the hexahydric alcohol solvitor by hydrogenation of the aldehyde group. So if you do the aldehyde group, the hydrogenation, I mean if you add the reduction, if you add hydrogen into it, if you do reduction, then it will come to alcohol. This is a famous rule of organic chemistry. And if you can because CHOCOOH, if you add oxygen, then you will go into the acid. So you can get the 1,6 anhydroglucose, 2,4 anhydroglucose, and 2 hexa hydroxymethylofulfurar. The hexoses can also be converted directly to the levulinic acid and formic acid. There are some other examples of gluconic acid, gluconol, lactone, sorbitol, sorbitans, mannitols, and different esters. Now question was asked from this discussion is vitamin C, which is the L-ascorbic acid, is perhaps one of the best example of commercial derivative of that is manufactured primarily by chemical synthesis. So the answer is given into this line that vitamin C is L-ascorbic acid is perhaps one of the best example of the commercial derivative of the D-glucose. So D-glucose, if you do the reactions, then it will convert into the L-ascorbic acid, which is the vitamin C. It manufactured primarily by chemical synthesis. So the process is also chemical synthesis. Here we are not using any biological route, means we are not using any microorganisms and enzymes over there. Okay, now lignin derived commodity chemicals. If we talk about the lignin, then it is a it is one of the important part of the lignocellulosic biomass, and so some lignin chemicals and their salts are derived as a complex mixture of compounds which you get from the spent liquor of the wood pulping industry. So you will get the liquors from the wood pulping industry which consists lignin in a major part, because in wood pulp they will remove the lignin out of it, and then it will, if you go to the some synthesis of chemicals, then you will eventually get the salts of it. These are the used as a commodity chemicals. Now the question asked is the DES are sold for a variety of industry and specially applications including adhesives, binders, dispersing agents, emulsifiers, cement and gypsum board manufacture, oil well drilling, and road stabilizing formulations. So which are the chemicals like glucose, lignins, sulfur and lactose? The answer is given in this paragraph. The lignins are sold for a variety of industrial and specialized applications including this all are these applications: adhesives, binders, emulsifier, and in this in cement industry it can be also used in the oil well drilling and road formulation. A few pure commodity chemicals are synthesized from the lignins, like vanillin, a member of the catechol series, is an example. The compound of pharmaceutical intermediate and flavoring and perfume agents. These are another applications to which can be produced from the lignin. Cinnamon alkaline air concentration of the spent sulfate liquors from the pulping operation. Okay. Then this is a lipid data commodity chemicals. There was no question asked from this from the assignment, and we not go into much detail. We discussed last time. So lipids are you basically we all know that fats which are found in vegetable oils and fruit pulps. So all the organic food items, if you are using as a biomass, you will get this lipid or fats. Or it's in the another case it will also available in animal tallows and greases, so which basically consists C6 to C24 fatty acid esters. So carbon chain of C6 to C24 in the form of fatty acid COOH, but it is converted into the ester, so it is in the COOR. So IH is replaced with another chain of carbon, so we can easily convert acid out of it. If you alkaline hydrolysis of the grease, and you can again convert this R into convert into the alcohols and aldehydes. So we get the mono and diglyceride and unesterified fatty acid. You can convert it into this. We already seen this how we can produce glycerol. So these are the different kind of chemical acid which is present, which is a saturated acid: lauric, myristic, palmitic, stearic, and bianic and all. Then monosaturated oleic and ricinoleic acid, and polyunsaturated C18 linolenic and eleosteric acids. Now as we discussed that this ester is converted into the acid, at the same time it can also convert into glycerol. So now glycerol is a very versatile chemical. It can be used in many ways, as well as it can sometimes use as a solvents, as some of the important solvent also. Okay. Okay. So we are discussing about week 11 assignment problems, and then we'll go to the week 12 discussion. So as we discuss about week 11 is all about the information. So if we talk about the lipid era comet, we discuss about pentose exercises and the questions asked from this, and lignin derived, and now it's a lipid derived. Important chemical is a glycerol, which has many different applications, hundreds of applications as it mentioned. It can be used in the alkali resin and the manufacture of explosive like nitroglycerin, glycerol trinitrate, and some ester is synthesized which can be used into the methyl esters and all. So now this have the many other applications. So we'll move through the next slides. Now it is a protein derived commodity chemicals. So protein derived means some, if you are using uh, plants and animals as a biomass, then you will get this polymeric chains of amino acids which are nothing but basically protein only. Amino acid, as we discussed, CONH2 is there. So, and it is in the form of polymer. If in the form of polymer in protein, so you will get CONH and then a long chain of it. So this is a polypeptide chains are converted into amino acid by acid alkaline enzyme catalyzed hydrolysis. If you do for the hydrolysis of it, if you add the water in the presence of acidic medium, then you will get the acid out of it, COOH. It is converted in COOH, and then alkali OH will be converted into the alkali, and enzyme yeah, amino acid by acid alkali. More than 30 amino acids have been isolated from the protein hydrolysates. Now these amino acids are important in in the application of the pharmaceutical industry, as well as some of the important beauty products and all. So most common amino acids are the glycine, alanine, serine, cysteine, valine, methionine, leucine, isoleucine, tyrosine, and all. The basic acid include arginine, lysine, hydroxylase, glutamine, histidine, and autin. And depending on this, most famous is the glycine, and it has many applications in the production also. At the same time, in the pharmaceuticals also. Okay, these all are from the protein hydrolysates. You will get it. Now, okay, this is so then we separately discuss last time also some of the production processes of some these commodity chemicals like succinic acid and butyric acid and 1,3-butene-diol, 2,3-butene-diol. So there was question asked for the succinic acid. I directly attached with the professor's slides. So succinic acid is basically COOH. So it's difficult to use this. So just bear with my handwriting. So CH2 COOH. This CH2 is again converted, joined into another CH2, and in this side again COOH. So this is actually succinic acid, and 4 carbon carboxylic acid, and this is a product of the anaerobic fermentation in the, and is also an intermediate of the tricarboxylic acid cycle. So then there are many applications of this, like 1,4-butanediol, tetrahydrofuran butyrol, lactone, and then methyl 2 pyridine and adipic acids. So even the US Department of Energy identify it as one of the 12 important promising fundamental chemicals to produce biotechnology. So it has many applications in the biotechnology, and it can be produced by the microorganism way, and helping with the microorganism, and fermentation and another process. So the question asked is, this is a 4 carbon dicarboxylic acid is one of the end products of the anaerobic fermentation and also an intermediate of the tricarboxylic acid cycle. So yeah, it is in the first sentence itself it is mentioned it is succinic acid, the 4 carbon dioxide carboxylic acid. If you want to forward a tricarboxylic acid, then you can add you can remove hydrogen and you can add COOH over here. So then it will convert into tricarboxylic acid. So that's already two COOH, two carboxylic acid are already there. So this is the answer, and it is mentioned in the first sentence. If you can't able to read on this slide, then you can able to read on this one. Now this is the route of succinic acid production, is the carbon resource usually be by using the phosphoryl pyruvate process. By using the enzymes, it will come into malate, fumarate, and at the end succinate. Succinate is the ion of the succinic acid. Then if you go for hydrolysis, you will get the succinic acid. Succinate needs to be hydrolyzed in order to get the succinic acid. In the same another route, a carbon resource acetyl CaO converted to citrate, then isocitrate, and after that you can separate it out, succinate out of it, and another product is a glyxylate. It will convert into malate and oxaloacetate. This also can convert into another products if you want, and again it will convert into citrate, and This is one cycle of the production of the succinic acid. In the another process, again you go down to pyruvate, and then you will do some using enzymes and biochemical processes. You'll go on to convert into citrate, and then it will the same isocitrate and succinate you will convert, and then again convert into fumarate malate in this cycle. Now this is how this succinic acid production process is taking place. First, whatever the biomass you will get, which will convert into D. First, we go into the R301. This is a deacetylation. So water acetic acid and another acetate are there, which will be removed, and then if you go by acid thermal hydrolysis. So in the presence of acid, hydrolysis process is taken place. And after that, as the addition of hydrolysis means you will add the water as a solvent in it. So you will get the two phase. One is a aqueous phase and another is a organic phase, which needs to be removed or separate in the decanter, and in the basis of density difference it will be separated out, and then you will go for the fermenter where fermentation process takes place. After that you will get succinic acid and other unreacted product as well as other impurities and byproducts that needs to be filtered out in the stepwise filtration process, which is first going into the microfiltration, which has a in the micron level particles will also be removed, more larger particles than that, and if you have nano level particle, then it will go into ultrafiltration after that, and then it will go for the multi-effect evaporation, where whatever the liquid is there, it will be converted into the crystallized, and it will go into the another waste will be removed out of it. And other than that, you will whatever the whatever the solid part out it's there crystallized, you go into crystallization, which is converted into the solid, and then it will go into the solid. Okay, so first it consists the semi-solid kind of structure, then you will go for the centrifuge. Liquid and solid will be removed. Liquid is your waste, and whatever solid semi-solids are there, it will go into the methanol purification and methanol evaporation. So it is methanol as a solvent, it will wash your final product and purify it, and you will get the succinic acid crystals at the end. And at the another thing, and you will use the multiple amount of methanol at the multiple stage, so you can again recycle back into the distillation and all, and you can again reuse again and again for that. This is how succinic acid production process is taken place. We discussed in the last lecture. Now the butyric acid. Butyric acid is the butyrics come from the butane, so it basically is four carbon. So it's four carbon, but it only has the one acid at one end. If you add acid at this CH3 convert into the acid, then it will convert into succinic acid. Now it's only one monocarboxylic acid at the end of the three carbon chain. So it's total four carbon carboxylic acid, and it's the oily colorless liquid. There's a question asked from this. It's unpleasant smell and acidic taste, and its derivative has been widely used in food, chemical, and pharmaceutical industries. So it's one of the important chemical, intermediate chemical when you order to produce many chemicals in these industries. So the acid form is also used to enhance the butter-like flavor in food, and the ester form can serve as a flavor in food or perfume. Butyric acid can also be used to synthesize the cellulose butyrate plastics for textile fiber productions, and these are some of the important derivatives production from this butyric acid. The question now that this is the question asked that gas can also be used to synthesize cellulose butyrate plastic for the textile fiber production. So textile fiber production, you can convert this cellulose butyrate plastics. The butyric acid is reacted with the cellulose, and then this will come into a plastic form. Then it will use in the fiber to give it provide it to the strength. So answer is a butyric acid. It is a butyrate. That's why. Okay. So this is it is come from this line. Now, if you again talk about the same butyric acid, so it's producing anaerobic bacteria. So, also been proposed a novel probiotic treatment of the inflammatory bowel disease. So, in the production, this anaerobic bacteria we are using in the in the absence of air, then whatever the product you are getting, which is also used in the novel probiotic treatment of inflammatory bowel disease. Now the question asks, there are many bacterial strains which are used in the production of the butyric acid, so which belongs to the genera uh, Xanella Clostridium, Butyribacterium, Butyrivibrio serina, Eubacterium, and many more. The Xanella Clostridium, Butyribacterium, and Butyrivibrio are the most studied butyric acid producing microorganisms, and however, the preferred strains are for potential commercial uses are in the genus Clostridium due to the higher stable productivity. And this Clostridium are basically gram positive chemo organotropic and strict anaerobic and sport farmers. So we gone through this what is a strict and facultative anaerobic, and it's the gram positive, it has a positive charge on it, and spore farmers and all. So the question asked is the same, which bacteria are the gram positive chemo organotropic and strict anaerobic and spore farmers. The answer is Clostridium sp. Now with regards to production process, and on the same, there was another question asked that the Geneva, Clostridium, Bacterium, and Vibrio are the most studied gas producing microorganisms. So butyric acid producing microorganisms, they are using for the production of the butyric acid. So it is mentioned in the same, this is the same discussion of the last slides. Now propionic acid production. So to see anyone is there, okay. Yeah, thank you for staying here, Sahana. Okay, so propionic acid production is first we take the nutrients which is come out about biomass, and then we use the water, and then we blend it into the feed blending tank. Then water feed will be going to the heat sterilizer. So sterilization processes remove all different kind of impurities and bacteria and microorganisms which are not useful, and then it will go sterile field will be go into the fermenter, which where the fermentation process is taking place, and you will get the CO2 out of it, and at the end this fermenter will be converted into the product which is a propionic acid, which will be for the separate of the propionic acid, which will be fed into the mixer setter extractor, where we first is the mixing process taking place, and after this is the mixing process, and after this settling process. So your chemical will be settle it down, and then still it is has solvent in tissue solvent in it, so solvent needs to be recycled. So this is a distillation column, which is acid stripping column. It's a stripping column, sorry, not distillation column. So stripping is suddenly strip the solvent out of its absorption kind of thing, and it's operated under a vacuum. And this is basically didn't mention by the professor, but this is for you to give some idea how this propionic acid production takes place. This is not only the single process where you can produce this propionic acid. There are many processes, there are different processes also available. So I am just giving you one example. From this you will remove these acids, and it consists basically acetic acid as well as propionic acid. You go for the purification column at the end, which is basically distillation column, and you will get propionic acid at the bottom and acetic acid in the distillate. Now another is a, we'll just glance to it because last week we already discussed. So another is a PLA production process, which is a polylactic acid. So basically it mentioned as a lactic acid which will convert into the lactose. Okay, so we'll not go to much detail. First it's a fermentation process take place, and then it's passed to the filter with impurities and other unreacted biomass will be removed. Then it will go to the precipitation reactor, and then reactor you will add different kind of uh, raw material required chemicals to it. Again it will go into the filter, then it will go to flash column where suddenly you reduce the pressure and expand the volume. Then it gas vapor and liquid will be separated out, then it will go into the pre-concentrated column, and then eventually this is like lactic acid, it's from the alcohol kind of process. So first for the fermentation will go for the esterification reactive process, then hydrolysis, and after that you will go for the methanol recovery. And because first we will get some methanol as alcohol out in it, then eventually it will go into the, because this is you can imagine this is not very easy process. If you go for the commercial level of PLA production, then there are many more process operations and processes are taking place. So after this, you will go into the oligomerization reactor, where you, because this is a polylactic acid which is the polymer, so you have to go for the polymerization, then distillation column for the separating out the solvent and all, and production reactor, distillation, polymerization, and at the end you will get final polylactic acid after the evaporation of all the other impurities. But now this polylactic acid, it is mentioned, but what are the applications? So this polylactic acid, it looks like this. It has many applications. Uh, if you go for the first, it's a biomass food, or if your food waste, not into the just application how it will, we are just seeing this kind of schematic diagram. This food waste is converted into fermentation and polymerization, you will get the polylactic acid. But actually into commercial scale, these many applications, these many stages it needs to pass through. So food waste, lactic acid, direct fermentation, you will get lactic acid. You will do the polymerization, you will get the polylactic acid. Now in the form of application, it is much more application is on is packaging. Why in the packaging? Because we are currently using the plastic is already banned in many of the countries and even India also. But there needs to be alternative of plastic needs to be used and fine for the daily applications. So PLA is a biodegradable plastic. You all heard about the biodegradable plastic, which is mainly come out from the polylactic acid. Then eventually in the future it will be replaced all the conventional plastics. Other application is drug delivery. So drug delivery in the sense, you whatever the drug you are taking, like whatever the drug, suppose you have taking the some like paracetamol or some simple drug, how it will be go into the actual if you have fever. So where are the fevers, their fever bacteria, or my is some viral fever are there, virus are there. So how it can be reach up to that virus, and how the that drug is fight with the virus. So for that one, some delivery medium is required. That kind of under the body we can use this PLA. So it will be converted into drug delivery system. Tissue engineering, your bone is broken and many other things happen. So sometimes before doctor, I used to put some metal plates. Now they are using this PLA plates. And if you heard about the artificial uh, heart or what you can say, pacemaker device and all, these all are made out of the polylactic acid. And then the common application is in the manufacture of different chemicals. It is definitely for sure. Okay, so in the simple word, lactic acid is a cyclic lacticide monomer. We have to remove water out of it, and we have to do the polymerization. You will get the polylactic acid. Another is a 1,3-propanediol production process. So we'll not go into much detail, but it is come out from the glycerol, which is a mother chemical from which this 1,3-propanediol is pro- produced. So as you can see, glycerol, why is it much more important? If you go by the etherification, then you will get the polyglycerol. Esterification, you will get monoacetyl glycerol. Because the dehydration, you will get acrolein. Hydrogenalysis, you will get the 1,3 and 1,2-propanediol. Oxidation, you will get dihydroxyacetone. Carbonylation, glycerol carbonate. Reforming, you will get synthetic gases. And acetylation, you will get cyclic acid. That's why glycerol is much more important. And 1,2-propanediol, 1,3-propanediol is also out of you get from the glycerol. So glucose is eventually converted into the by this enzymatic route to glycerol, and then it will convert to 1,3-propanediol. Same in the other route if you are using it, and ATP dependent glucose transport and PP dependent glucose transport. So you will get that and glycerol 1,3-propanediol out of it. So glycerol, if you remove the acid, then it will convert hydroxyacetone and 1,2-propanediol. If you remove the water, not acid, in the presence of acid. So if you go to this route, this OH is at a different position, this OH is different positions. That's why it causes 1,3 propanediol, 1,2 propanediol. Now 2,3 butanediol production process. So there was a question also asked from this one. So 2,3 butanediol, basically we know styrene butadiene number that is used to 3 butanediol, butadiene and all. These kind of chemicals are obtained from this butanediol. So basically is a commercial interest of the anti-freezing agents. So what is an anti-freezing agent? So it has a low freezing points, like water has a freezing point at 0 degrees centigrade, around 0 degrees centigrade, you can see. But if you add these kind of chemicals into it, because this chemical is not solidified at 0 degree temperature, they let not water also to be solidified. So these are the where are the applications. So if you are using some water cool or liquid cool chiller, liquid cool chilling units and all, where if your water is good solidified, then the instrument will be damaged. So in there you will use these 2,3 butanediol and different kind of chemicals into it. So it is basically 4 carbon diol with hydroxy groups at 2 3 carbon positions. So like this OH at 2 and 3, 2 and 3. And now depending on to the where this OH is attached, it is either D 2,3 butanediol. D is means uh, uh, this the OH from down, first OH is in right side, if it is in left side, it is L. And then if we go for the meso 2,3 dione, where both of the OH either of the left or right side is it's similar sides. Now if you see the properties of 2,3 butanediol, it is also known as 2,3-butylene glycol, 2,3-dihydroxybutane, and dimethylene glycol. Now the properties is high boiling point of 177 degrees centigrade, low freezing point of -60 degrees centigrade. That's why it is using as an anti-freezing agent. Now the question asked is, this is a commercial interest as an anti-freezing agent due to its low freezing point and as a feedstock for the formation of methyl ethyl ketone by dehydration. So it is mentioned from here. Okay, so and another, okay, this is anti-freezing agent in the first sentence itself. So answer is 2,3 butanediol. Now how it is produced in this enzymatic way, it is lactose is converted into the glucose and galactose. The glucose it was converted to butanediol. So happen. Now this is a process. It is going to fermentation process. Out of it, sorry, mixing tank, and after that it will go into the some holding tanks, and then it's go to bioreactors where reaction is taking place. And after that it will go, and after this reaction taking place, you have to remove the impurities and unreacted product. Then it will go into the rotary vacuum filter in the filtration process. Now in the continuous reactor and decanter, you will get this methyl ethane ketone water ethanol, which is also produced in these reactions. So you have to remove it, and then after that you will go for the amica recovery out of it, and you will get this distributed in between. Okay. So about amica recovery, so you will get your product here only. It's, yeah. So PHA production, this is which is also one of the important chemical, because this is a polyhydroxyalkanone. uh, so now it's basically, if you, it depends on how many chemical monomers are connected. So poly means obviously it is a polymer, but if you have short chain polymer, then it looks like that. If you have many more medium chain length PHA, if you have short chain length, it means in between the polymer also this R is there. So how many carbon chain is available in that? So one is a mono C4, and then two chain is there, the total 5 carbon is there. That means it can move up to 12 carbon chain in the presence of this R, and then it will got polymerized. Now how it will form? So nutrients and other go into the bioconversion in this bioreactor, and after that products air will be going to the, so it's aerobic process, and whatever exhaust gas which will be removed, if the production will be taking place, you will get your product. It will be separated out in the help of centrifuge, and you will add some basic water. So water in the presence of some base, strong base, and then it will go for the extraction purification process, and you will go for the add some ethanol. You will get the PHA, and you will go for the wastewater. Other than that, so whatever the now this is the uh, integrated process where this exhaust gas which you will send to the uh, in this biogas production, where this can be again used into for to generate electricity, exhaust gas, generate electricity and heat. Okay, so now we move through the now all the questions of this week 11 assignment problem we discussed. Now we move towards the week 12 discussion, which is the integrated biorefinery. So here biorefinery we already discussed that it needs to be some kind of process where you are getting the many different kind of products in the similar kind of processes. So like if you talk about the crude oil, then we have crude oil. If you go with the refinery, then you will get the range of products out of it. So now what is the similarity? As crude oil is also consists many kind of different chemicals into it, which is coming on from the earth crust, and it will convert into petroleum products. Similarly, if we talk about this biomass, then biomass also has the various different kind of chemicals products in combined together only. So it can be also you will get the number of chemical products out of it. So it is working as a similar to the refinery, but this is not a petroleum refinery, so we can give the name as a biorefinery. So it is already discussed. Now the integrated biorefinery means how one kind of product is integrated to all the one kind of biomass is integrated to all the products, or one kind of two kind of products are integrated together, and how it is converted into the various products in with the help of biorefinery. Give me 2 minutes, I just want to drink water. Okay, no one is there. Oh, matlab sorry. Okay. So this integrated biorefinery, if you see, this is the more similar from the crude oil refinery. As a so crude oil refinery, you have the fossil oils, crude oil. Then you heat into the heating so furnace. Then it will go into the fractional distillation column. Okay, so where you will get the different fractions out of it. So in the top fraction you will get some particular degree temperature you will get the gas. After that you will get the gasoline, kerosene, light oil, heavy oil, and asphalt oil. And then out of these whatever the oil and all which you go with the chemical process reactions, and at the end you will get some fuels and chemicals out of it. So this is how this crude oil refineries work. Now if you talk about this biorefinery, then it is known as a green innovation, where this biomass is going to the biomass pretreatment, enzymatic digestion, fermentation, and this bio process we generate the carbon dioxide. Here also you will generate carbon dioxide, but this carbon dioxide is again used for this biomass to in the photosynthesis process and our process, and it will be again recycled back like this. And this you will at the end you will get the biofuels as well as biochemicals. This is the fuels and chemicals. These are from the bio originated. That's why it is known as biofuels and biochemicals. Now, if you want to understand the biorefinery in the larger context, then this is a wastewater or some affluence of the chemical uh, processes and all. So if you just this is one of the process like where we are using the algal biomasses. So we wastewater and all we are using and we are going for the algal biomasses. So wastewater consists lipids, pigments, carbohydrates, and proteins. So this information I'm giving for the work, your knowledge and information. It is not exactly same which is discussed by the professor. I gave you some different sources, so you will get to know different kind of processes and different. You will get some information which was important for your understanding. So for the exam point of view, you have to just prepare what professor already taught. So this agar biomass will be go for the pre-treatment, which is from the sonigation, microenzymatic, hydrothermal, many kind of pre-treatment which we already have gone through. Various kind of pre-treatments are there, and after that you will go for the you will get the carbohydrate out of it. If you fermented, if you go to fermentation, you will get hydrogen, methane, ethanol, lactic acid, and enzymes. And then whatever the lipid part of it, if it is there, which is a fat, basically it will go for the transesterification. You will get the diesel out of it and glycerol out of it, and we already know what are the applications of glycerol is. So it is used for the many more applications, but there is one application which is mentioned. If you go for the fermentation of glycerol, you will get the beta lactic acid. Then what are the proteins which there, which will be converted into chelate, fuel, fertilizers, and what are the another effluent is remaining, it again go to the wastewater. So this is always biorefinery is a cyclic process where you will start from something and at the end you will get the same thing at what with the thing which will be connected with your first part itself. Now integrated biorefinery. So this is also small cartoon where you can see that how it is integrated biorefinery. So first we'll go through this biomass, and from this product we'll go for the first synthesis. So how it is integrated biorefinery design, how it is constructed. So first we go for the process synthesis, and then process design and innovation. So mainly in for this it is used for the pulp mill. The pulp mill, out of that you will get some product out of it. It will be used into this integrated biorefinery where you are getting the biomaterials, biochemicals, electricity, biofuel, and how this biofuel and electricity will be generated. So you are using this pulp mill. One portion is into convert production of the biomaterials and biochemicals. Another portion is you use into the bioenergy plant, which where you are using this biomass to convert into the energy and heat and heat electricity. So you will get the biofuels as you use it at the application of biofuel. So this is using as a fuel, so it's a biofuel. You convert into the energy, which is basically electricity, which you will use for the running this integrated biorefinery. And there are some products which are non-reactive, which you can again take it to the biology plant. So this is how this integrated biorefinery concept work. So everything is got integrated with one another to get most optimized and techno-economically sound use of your biomass processes. Now there are some definitions. So this concept of biorefinery was first originated in the late 90s as a result of scarcity of fossil fuels and increasing trends of use of biomass as renewable feedstocks for the production of non-food products. So as we all know that fossil fuels are depleting every year, and very less uh, is available with the future generation. So then people are thinking about to produce some chemical which are basically for the chemicals which are used as a similar petroleum product, but which are converted from the biomasses. So that's how this biorefinery concept was emerged. And there was a green biorefinery term was first introduced in 1997, where the definition is green biorefineries represent complex to fully integrated systems of sustainable, environmentally and resource-friendly technologies for the comprehensive material energetic utilization as well as exploitation of biological raw materials in the form of green and residue biomass from a targeted sustainable regional land utilization. This is a very wordy definition, but you don't need to remember, I guess. This is what looks to be a big actually terminology, but this is what it was coined as the definition of the green biorefinery. So integrated systems, very sustainable environmental research friendly technologies will be used for the comprehensive material. So material which will be produced out of this, which are much more comprehensive, which are much more applications, and which are going to use energetic utilization. So as we have seen the last slides, so energy what we are getting, this is also converted in some of the other and the processes of the biomass related processes only. So the American National Independence Laboratory is a famous NREL. Defined biorefinery is a facility that integrates biomass conversion processes and equipment to produce fuels, power, and chemical from the biomass. As we saw in the last slide, it is used for the production of the fuels, powers, as well as chemicals from the biomass. If we talk about the integrated biorefinery, then USDOE, which is the United States Department of Energy, which is and the this National Renewable Energy Laboratory (NREL). Further, this mechanism technology based on fire platform. So there are various fire platform where you can convert this biomass into the products. So biomass conversion technology platforms. One is a sugar platform biorefinery. Another is thermochemical or syngas platform, and the third biogas platform, which is basically anaerobic digestion process there. Then carbon rich change platform and plant products platform. And the same way, this integrated biorefinery feedstocks will be converted into the three different phases: phase one, phase two, and phase three. So phase one is a one crop feedstock, which is a one process. Example, biodiesel from the sunflower seed. So we are using the one similar one only one kind of plants or vegetable for this. So you will get the single product out of it. Then if you go for the second phase, then which is a one crop feedstocks, it is also one crop feedstock, but processes are multiple processes. Here you are following on one processes. We are following the multiple processes of the same feedstock. You get the polymers, chemicals, biofuels, vitamins, polyols from cereal grains or maize, and you will get the range of products because you will go for the many different kind of processes. And in the third phase, you are increasing the feedstock from single to multiple. So this is a mixed feedstock of low value biomass and multiple processes are there. Then you will get the range of products energy from the ligno, like this example, lignocellulose and food industry waste. And at the end, you will get the range of products. So basically, mainly these two options are useful in the biorefinery integration. Then the phase three is much more appropriate option. Okay, so this is how this integrated biorefinery can be worked out. So biomass is first is go in the densification, increase the density, then you will go for the extraction process from the extraction of chemical and residue. What residue is there, you will go for the biochemical processing or thermal processing, and out of it you can directly convert into some chemicals and materials, or you will go for this biochemical thermal processing and then you will get some chemicals and materials out of it. For now, for this biochemical process you require energy. Okay, any kind of process you require energy. So this energy is provided by the combustion process. Now is combustion process also you have to use something for combustion. So these all residues are there which will be used for the combustion. Now when the combustion happens, so you will get the energy. That is a good thing. You will use the energy for thermal process or other step of process, but at the same time you will get the much more amount of carbon dioxide. So this carbon dioxide is again fed to the biomass, and biomass is utilize this carbon dioxide and for its development and growth. Sorry. And this combustion will also give you the energy which is not being used in the plant. You can use it for the commercial level. Now give me one sec. Now this product derived from the biorefinery. So now energetic products and non-energetic products. So if we talk about energetic products which will give you the energy, which are solid energetic products first. And first there are three types of energetic products: solid, liquid, and gaseous. Because solid energetic products, these are the pellets. Or liquid energetic products, these are the bioethanol, biodiesel, bio-oils, and biobutanol. And then the gaseous energetic products, which are biogas, syngas, biohydrogen, biomethane. If you go for the non-energetic products, then by using building block chemicals, using the oxosynthesis, isosynthesis products, polyphenols, pigments, bioadhesive, and one for succinic acid, fumaric and malic acid, glycerol, sorbitol, xylitol, or fisotose liquids. Then the other is the packaging films and coating, where we already see that PLL last lecture. Polylactic acid, co-e-caprolactone PCl, polyhydroxybutyrate PHB. It will be used for the packaging films and coating. Then there is a therapeutics and the nutri- nutraceutical compounds, which will go lipid based, carbohydrate based, and protein based. Now there are some examples which professor also mentioned, that this integrated biorefinery, which is from the single feedstock. So if we talk about the one of this such a feedstock, which is a corn. So this is the example of the integrated corn based biorefinery. Now why people are using much more corn? So this is the report from the DuPont. It says DuPont Nevada, so making cellulosic ethanol a reality by the numbers. So why its corn is important? So this is why the most of the ethanol produced in the worldwide, which is from the corn itself. And this is a slide from the DuPont. DuPont is a major chemical industry, one of the top three chemical industry around the world. So DuPont Nevada site cellulosic ethanol facility is expected to be completed in mid 2014. It's very old news, but you can see that they build a major economy out of it. Situated in prime agricultural location, this over $200 million facility will be among the first commercial scale cellulosic biorefineries in the world. So they converted the corn-based biorefinery in the year of 2014. So now the corn store harvested was in this 1,90,000 acres, which will be, this is for example, it will be corn store bills will convert 5,90,000. Then feedstock will be supply up to 30 miles, and then corn store and supply radius this to this area, you will get this 30 million gallons per year ethanol production. And 150 gallons per acre is a additional ethanol so you have inventory. And then other than that, this corn will be used for the energy production, energy supply and transmission, everything. That's why this is a kind of a refinery. And if you see the professor explained the details about the corn based biorefinery, I will give you the small process over here. So corns are there. First we'll go to the pretreatment, mechanical pretreatment of hammer mill. Then it will go for the meshing process. Then after in meshing, you will go for the alpha amylase cooking in the presence of alpha amylase 95 to 100 degrees centigrade. And then it is converted, go for the liquefaction, where you go for liquid. And then simultaneously you will go for the saccharification and fermentation process, as we discussed earlier, SSF process. Simultaneous saccharification and fermentation process. So for you will get glucomylase at 45 to 60 degrees in the saccharification process. You will use the yeast for the fermentation, and then you will get this ethanol alcohol out of it. So you have to go for the distillation process for this alcohol. So you will go for at the distillate, you will get the product which will be separate from the molecular sieves, and then you will get the ethanol. And then another liquid liquor is there, it will go for the centrifuge. Then you will have some solid powder out of it. The solid powder will be gone for weight cake, which will go for the livestock feed for the various animals like kettles. They again convert it to the manure. This manure will be go for the anaerobic digestion. You have the liquid out of it. Remain that liquid again you use it for the meshing process, and this solid manure and liquid will go for the anaerobic digestion process, and at the end you will get the methane gas, which can be used in the in plant for the energy production and all. And another effluent is there if we go for the land application. That means it will be used as a good source of nutrients for the lands. Now integrated soybean. So after this corn, the professor again discuss about the soybean. soybean based biorefinery. So here you can see the soybean is there. So first it will go for the cracker. This is also example. There are many other kind of processes you can see. So soybean cracker, conditioner, flake and expander. So soybean will convert into this kind of pre-treatment. First it will pass through it, and then it will go to micellar desolvenizing, oil extraction out of it, and then defeated mill desolvenizing, right? Say desolvenizing, and you will get a defiled the soybean meal out of it. Other than that, you will go for the process. If you isolate and process, then okra whey and soy protein, as you know, soy milk and soy protein, soy whey, which will be produced. If you go with the concentration of the soybean protein concentrate and soybean molasses, you will get it out of it. Other than that, you will go for the desolventizing and degumming, and you will get the crude oil out of it. First step in the and degumming, you will go degumming centrifuge, then you will get the soybean lecithin, which is a kind of amino acids which is useful. And then another process, you go for neutralizing, pitching and deodorizing, refining of this uh, degumming, then you will get the refined oil of the soybean refined oil. Or in this way, soybean first harvest and whatever store is then soybean seeds, and the seeds will be go into the preparation. Soybean flex into converted to flex, go for the extraction process, and there are two ways. One is a crude oil plus hexane extraction. Okay, I will get after the extraction you will add the hexane as a solvent, so you get the crude oil plus hexane. Go for the evaporation, then hexane will become back. We will again recycle back into the extraction process, and then crude oil is there for the degum oil, neutralize oil, bleaching, deodorizing, refined soybean oil, and another deflated flex are there, the same like this. So it will go again the operation hexane will be get deflated soybean meal isolation, you will go okra whey soy protein isolate, and if you go for the concentrate you will get soybean molasses and soy protein concentrate. So it's just same to same like this process. So here is the pictorial representation, here is a block diagram. Now integrated soybean based biorefinery. So how everything is got integrated, like we saw that how integration take place, how we can use these processes internally to use for the fuel, energy and everything. So the start from this here, so I mean plantations harvesting take place. Straw is there. Straw is called for the cogeneration system for making transition the energy, and then you will get not only straw, many other products which from these processes will become, and it will go for the this heat and energy production. So you will get the steam and electricity which will use in the next step or process of this soybean. So raw seeds, whatever the harvest is there, we go for seed preparation, oil the extraction and myself desolvenizing. Oil extraction process is there. Myself desolventizing, and then solidification is go desolventizing. Then in this oil extraction process, the electricity and steam provided by the this cogeneration system only. You will get the defeated meal, which will come to desolidizing and concentration carbohydrates, extraction, desolidizing and dyeing and SPG, soy protein and all. And after that, you will get the crude oil out of it. That crude oil will go for the refining process, go for the refining, and in the refining first the degumming. What is degum oil you will get? It will go into the neutralizing, bleaching, and deodorizing, and you will get a refined oil out of it. In between, if you remove it, the between, so gums will become drying, and you got the lecithin out of it. And this deodorizing, if you remove it from the concentrate, you will get the tocophenols out of it, tocopherols. And in between, from the different step, you remove it. The substrate saponification, esterification, biodiesel, refining, glycerol. You will get the glycerol and biodiesel out of it. We want the finishing part. If you go for esterification, transesterification, again you will get the glycerol and biodiesel out of it. In any step, you are taking the oil, crude oil, and you go for the transesterification, saponification, emulsification process. In the step, then you will get the glycerol and biodiesel out of it. If you require the energy, electricity, steam, it will be supplied by the discouragers. It's so in the deconsolventizing and all, you will get the molasses out of it. You will get use in the cogeneration system along with hulls and straw. and you can use the makeup water out of it. In this process of water will be also, if you get the water inside it, you can use again into recycle. Surplus electricity you can give use for the other applications. So this is whole use for how it's indicated by refinery of its with knowledge. The integrated sugar can burst by refinery. Sugar is basically sugar cane bagasse is there. First we go for the hydrothermal fractionation. We'll get the solid and liquid. So solid will be converted into cellulose first, then hydrolysis, and then you go to glucose, oligosaccharides, and gram glucose. You will got many different products. So, and for this hydrothermal fractionation, you can use the ionic liquid, or many other solvents out of it for this process. Or you will use the solid acid catalyst synthesis. SiO2 is SO3H, SO2 minus TiO2 Fe3O WO2 sulfonated bentonite, and that's a catalyst which we are using here. So this is all catalysts are there. So which will be first characterized using this Fourier transform infrared spectroscopy FTI method, X-ray diffraction, which is XRD method for the crystallization of zinc. FTI will be so the which kind of organic groups presence are there, be it is for the surface area. Then this liquid and solid as we discussed what this liquid you will convert the hemicellulose plus lignin, and lignin extraction is there, so lignin will be converted to pyrolysis, and pyrolysis of lignin you will get the biol plus carbon mass microsphere. And if you have this hemicellulose, then this is the step where hemicellulose and the ionic liquid are together to combine this one with the extraction. You will get precipitate hemicellulose ionic liquid for recovery. Then you can go for the various chemical products out of it. Now we see the sugarcane residue, and you will get the energy, saccharides, enzymes, organic acid, ethanol, lipids, food, fuel, proteins, biopolymers out of it. On the other end, if you have first generation sugar, ethanol means sugar cane, you have the juice, sugar, and ethanol. The ethanol is good for the wineness. We are using the wineness enzymes, molasses, enzyme, bagasse, and straw, molasses, bagasse, straw, and vinous. Venus, you have that you got the sugar cane residue, and you will convert into this many products out of it. Now integrated soybean and sugar cane based biorefinery. So as you can see, sugar is there. So this in this biorefinery you are using the soybean sugar and both together only. So intercropping. So you are in the same field you crop the soybean and sugarcane, and go to the biorefinery. You will get the soy meal, hulls and lecithin, glycerol out of it, cellulose nanocrystal and nanofibrous biodiesel. Again, also get sugar, ethanol, biogas out of it, electric energy out of it. Now, how we will get? You already know the 12 chapters before 11 chapters, and in which process, which kind of process you are using for the which kind of products you already know. That's why we're not going to the detail of it. Okay. You want to get the detail, like we had this integrated soybean sugarcane based biorefinery. Okay, so this is agriculture stage where you have the sugarcane thresh and soybean oil stage. So biodiesel they digest a vinasse as agriculture stage. You will get the sugarcane thresh out of it. You see that soybean is there. Soybean is first for go for the oil extraction where soil lecithin, soy meal, and soy hulls you will get, and oil extraction you transfers the biggest, and you will get the grease roll, phase separation, and at the end you will get the biodiesel out of which the biodiesel production is there. So I go to the not going to the much more detail. If you go for the sugarcane, soybean is there. Trace is there which you go for the third application, but the sugarcane, your juice extraction. If you go to ethanol stage, and the first juice is concentration cooking and centrifugal drying, and you will get the sugar and sugar juice. Sugar stage is there. So other than that, you go to juice, and juice is a sucrose, glucose concentration, fermentation. You go to using the fermentation treatment here in the east. There you go for filtration. East will be recycled. Wine HM will be there. Then go for the ethanol production, ethanol purification, and then you will get the ethanol. So once ethanol, again wine is there. It will go for anaerobic digestion, and will at the end you will get the biogas. So biogas is a biomethane. You will get the combined cycle which will gives this gas. Will be biogas will be used for the production of electricity and energy which can be used on the inside. Again go for the combined heat and power production for the plants. Now we talk about this is all about the 1G ethanol. This is the 2G ethanol juice, a 2G ethanol stage. So this is juice extraction. We'll go for the bagasse and all. We'll go for the pre-treatment filtering, hydrolysis separation. You will get the unhydrolyzed biomass. In between, you will get the hemicellulose. Hemicellulose is converted into fermentation and go hem white hemicellulose white biogas. But at the same sugar stress and bagasse milling pre-treatment and you go pre-saccharification and simultaneous saccharification and fermentation process. You go for this filtration, again you will get the ethanol out of it and you will use it. Cellulose nanomaterial stage where the unhydrolyzed biomass is delignified. Hydrolyzed purification you will get cellulose nanomaterials. And again you have this bagasse, you combine it and power generation as you can use it into the biogas bagasse lignin out of when you will get the steam and energy out of it. You can go through it. I will send this way. Now integrate algal lignocellulosic biorefinery. Okay. So microalgae state. So vitamins and mineral, lipid, proteins, functional food ingredient, pigments. And if you go for the processing, then separation, solvent based extraction, saponification, separation, extraction, separation, elimination from the products, you will get this vitamins and minerals. You will get aspartic acid, beta complex, potassium, sodium. And if you go for the lipids, you got the PUF is into nutraceuticals and health promoting substance. Proteins will contain essential amino acids and lectins and all. And pigments will convert into carotenes and cyclogens. TGS carbohydrates. Then the functional ingredients will be algae, biotic production, transnification, TAGs, specialty chemicals, carbohydrates, get the syngas, biogas, gasification, anaerobic digestion, biogas, oil, liquefaction. The food industry and all you will get like this. Okay, so this is how maybe you cannot able to do it, but I will make you know. So this is a biomass type, ignocellulosic biomass and algal biomass. You can merge it both together. First, then is the process type. First is the biochemical conversion. You merge it both together and do a primary process, fermentation, anaerobic digestion, and enzymatic hydrolysis. You get the primary product as ethanol, butanol, hydrogen, biogas, and reducing sugars. And then secondary product out of this same product you get the solid fuels, uh, animal feed, CO2, ethylene, biomethane, CO2, methanol, olefins, alcohols, organic acid, and microbial biomass. For the chemical conversion, secondary product you get chemical hydrolysis, supercritical treatment, and solvent extraction are the processes. You get the chemical process glucan, xylene, pentosis, hexosis, lignin, supercritical treatment, glycan, xylene, pentosis, hexosis, solvent extraction, lipids, glucan, xylene, reducing sugars, biofuels, organic acid, solid fuel, same biofuels. Thermochemical conversion, then gasification, syngas, chemical fuel, biochar, bioil, methane, pyrolysis, biochar, bioil, fuel, thermal friction. You got purified biomass, biofuel, combustion, steam and heat. You will get the electricity, heat, mineral acids, liquefaction, and bioil, fuel, biochar, light gases. Mechanical conversion, milling, grinding. You'll get the milling, grinding. Get the small size biomass, fuel, chemical product, absorbance, pelletizing, briquettes, spit. You get the fuel and heat out of it, pressing. Lipids, solid sugar, and biofuels, forms, dyeing fuels, chemicals. Get the biofuels, organic acid, polymers, heat, and electricity out of it. Now the algal biorefinery. So as you can see, there microalgae is there. So microalgae is converted, and if you go to the new converting nutrients industry, domestic and commercial, then these nutrients will be converted into everywhere. So wastewater from different sources, commercial, domestic, industry, it will convert the nutrients from microalgae cultivations are there, and harvested biomass then it will, these nutrients will be converted into, with the help of microalgae, converted to nutrient biomass. And biomass before pretreatment looks like that. After pretreatment, now the biochemical conversion you can separate out. So anaerobic digestion will get the biomethane, dark fermentation will get the biohydrogen, yeast fermentation will get bioethanol, fermentation will get bioplastic. Now this is how it is look like. Okay, so okay, so wastewater nutrients. Yeah, so anaerobic phase you will get the NPK, and your nutrients you will got converted. Microalgae cultivations there with the help of sunlight. Microalgae will be used for the harvest of algal biomass protein. Protein will be taken animal feed. This this mechanical process, the oil algal biomass, you will get the mechanical, chemical, combinative, biological, physical processes. The organic waste biomass will be going to pretreatment. So this treatment after the sugar is hydrolyzed, and then it will be eventually will get this carotenoids and pretreated solid residue, bioplastic, polyhydroxyalkanoates, and Capes vector. Other than that, by using this anaerobic digestion, you will get digested biomethane, which are again used as a biofertilizer digested and going on. This after this solid residue will go for the anaerobic fermentation. You get the bioplastic, dry fermentation will get hydrogen, yeast fermentation will get bioethanol and sugar out of it. Then this the biomass will be extracted, repaired out of it, go for a transesterification, and you will get the biodiesel out of it. And whatever this the vegetation and all, you will get the biomethane and all, you will go for the effluent and all to construct a wetland and combined heat and power generation unit where you use this biomethane for producing the heat and electricity. Now waste biorefinery where you use the waste. So waste biorefinery, zero waste biorefinery. Then it is first is a resource correction and processing, so reducing dependency on existable feedstock, raw material, virgin recycle. Another is production and distribution. So minimizing resource consumption as well as reducing greenhouse gas emission by using renewable energy and alternative raw material. Then you will go to consumption and use, reducing waste and extending life cycle by reselling, remanufacturing, repairing and upgrading. Resource recovery, whatever the recycle resources, replacing end of the life concept and lowering the pollution residual waste. So this is how it is looks like waste biorefinery. It has a petroleum based linear economy and this bio based linear economy. So this is all about the refinery, which is an non-renewable energy production. The non-sustainable processes are there, and this environment impact is there when you are using the normal refinery. But if you transition to the waste biorefinery of the bio-based circular economy, where you have the renewable clean energy sources, your process is sustainable in the nature, it is ecological environment friendly. Now, if you see the sum of the figures, in 9.5 gigatons of carbon dioxide per year, it will produce by this normal refinery, 650 kilometer cube water per year. It is generated at the same time. 2.2 gigaton of solid waste per year it is generated. So that's why this bio-based circular economy will be much more useful to mitigate all this problem, and as well as you will get the sustainable process with the help of environmentally and ecological friendly process. Other than that, this integrated waste refinery, how it is look working. So first of all, this biogenic fraction is there, which is converted into acidogenic fermentation process, and you will use the alcohol, medium chain fatty acid, alkenes, and polyhydroxylates. We'll get the hydrogen and methane out of it, and then we go for the bioelectrogenic system. When the cathode and anode, we are using the electrolysis of bioelectricity, and you will get the biofuels, biogas, and resource recovery. To this bioelectricity, we go for the bio and oxygen cultivation, and your bioplastic, bioelectricity, biohydrogen production out of it. Over the VFA, then polysynthetic cultivation, you got the biogas, bio-oil, biochar, and biofertilizer. If you go with hydrolyze this one, then you will get the alcohol, estrogen fermentation, you will get the alcohols, medium chain, fatty acid, alkenes, and polyhydroxylates. You got the biowater, treated water, biofuels, bio-based products, and bioenergy at the end. Now there are two important concepts which in detail purpose I explain, but due to the time constraint, I will not go into the much more detail of both of the topic. So one is a techno-economic analysis or technical assessment, another is a life cycle assessment. So techno-economic assessment, if you just see the example how it is working. So basically any biorefinery has a three different size. One is upstream, another is midstream, and at the end the downstream demand sides. So downstream are actually it's a demand of the product which is moving by using this moving gun. If we talk the supply, that it is about how it's which kind of feedstock and which stock cost is there. So when you go for the techno-economical assessment, then you have to first uh, understand the requirement of all the upstream supply side and downstream demand side. So you have the feedstock supply, feedstock cost, so which is your feedstock, which you have the lignocellulose, for example, signocellulosic biomass or different kind of biomass. Then you have to see for the moisture content. So moisture content is very useful for the one of the important parameter to qualify for the process production and all. So in that for the integrated techno-economic assessment, you have to go for the market study. Market study will be given for the primary product demand in the upstream side where the product price, when final product will be taken, product will be called product price and product demand out of it. You see the search the understand the market study. From that you will go for the raw material utilization. And this marketing study will be go with the technological assessment and economical assessments and how much kind of technology is required to produce this kind of product from this kind of feedstocks. And out of that, what is the cost which is involved in the production of this one. So information is give and take at each and every step of this. And then you will go for the sensitivity analysis, which will be optimize your inflow and outflow of this whole refinery process. So this is how the simply it's a techno-economical analysis assessment is taking place. So it's in very simple language, not much detail. So if you see the information flow is always between the market study, technological assessment, economical assessment, and sensitivity analysis. Now the technological assessment, if this market study, we all can understand that which kind of product market fit is there, and which kind of for this market, which kind of must we need to use it and all. Then sensitivity analysis is more or less how to optimize the process with fewer objective functions and constraint. How can we optimize the overall problem statement. This is all about. Now the main thing is technological assessment, economical assessment. So this is much more in detail we need to understand. So you have to identify some of the input variables like quantity and price, and there are some variables and some variable moisture content and all. You have to go for the process flow diagram for it as a chemical engineer. You go for a PFD in mass energy balance for to understand the technological assessment. So whatever reason to first for diagram mass energy balance you will get, it will convert intermediate variables, and then it will be used into the economic assessment. So for this product process is how can economically uh, use the different sorry economically. Okay, so today in today's lecture we already discussed about the 11 chapter assignment problem. This is 12th chapter and this is the last slides of the 12th chapter. So this is all about techno-economical analysis, which are the main four thing we have to keep in our mind for the techno-economical analysis. One is the market study, technological assessment, economic assessment, and sensitivity analysis. Market study we can do understanding the market requirement, what is the demand of that one, and what is supply of that one. And sensitivity analysis where we are doing the optimization of all this technological assessment, economic assessment along with the market study. Now in detail, if you go for the technological assessment, then we have to identify some input variables like quantity and price, and some variable like moisture content and all of our feedstock and how much it will be uh, depend on our product quality. So process flow diagram, then we are as well using the chemical engineering uh, uh, steps where you generate produce a process flow diagram, do the mass and energy balance, and what are the output you are getting from these steps you are using as an intermediate variable. And in order to go to economic assessment, in economic assessment, you can go for the capex. Capex is the capital expenditure for these different steps which are there in the process flow diagram, like reactor, separation, and all. You have to go for the how much cost is required for this one, the capital investment you have to perform for this. Other than that, for this operating of uh, this whole process, you require some operating expenditure, which is known as opex. And for this you have to perform the feedstock cost, hydrogen cost, and all other costs which are there. And out of it, you how much you profit you will get, which your revenues, you have to convert into revenue streams. And these all are to convert into the functions, and then these functions needs to be optimized in order to have the output available, like net positive values and internal rate of return and all, which all discussed by the great detail by the professor. So I am not going into much more detail in all these things. So this is how all the economic assessment and value out of it you will get it, and it will go into the sensitivity analysis, where you optimize the or each and everything according to the other information which you got from technological and market study. Now this is the last slide, and the life cycle assessment. So life cycle assessment is basically, if we just see the different approach which be taken place if in the life cycle assessment. One is a QSD approach and information handoff. So specify decision variables. So in the life cycle assessment, basically you have to understand the process of from the cradle to a grave, that how much these process steps are, how exactly how it will be processed, and how what are the factors which is associated, and what are the parameters we need to take care of it. So first you have to decide variables we have to find out, so which is the independent parameter for define design and operation of our processes. For these variables like unit operations, operating pressure, retention times, the cycle times, like this. So in our processes, these are the much more critical parameters which are the decision variables, which is known as a decision variables. First, and then another is the defined technological parameters. So value or ranges of parameter to define unit sizing and performance. So like if you talk about the technology parameter like product yield, maximum data efficiency of unit operation, and these all things are required again, because which is all your objective, that how much is your capacity of my plant, how much product quality I will get, and how many operations I require to get that amount of product quality and that much amount of product yield. And then for the define the contextual parameter, like all non-technological factors that influence refinery sustainability. So it's not sometimes the context, we need to understand the context also. So that is basically not any technology is in taking playing any role over there. But suppose it's biorefinery location, this is whether it is near to field, whether it's near to the customer or not. Now, what is the feedstock composition? And if you change the feedstock in one place to another, what are the impact of this thing? What is the scale of our systems? What are the policies which are made from the governments? So all these three design variable, technology parameter, contextual parameter, you are taking, and you will use this into the output and matrices of the conceptual design defined scenarios. So to see for the biorefinery design, process layout, location, polishes, along with this, this is kind of design which is much more optimized and very well defined, which can be used for your life cycle of all of your biorefinery. After that, you can go for the establish design algorithms. So after this, all the factors and variables and parameters you will get, you can go for the algorithm building. So which is system of equation to automate the design of the biorefinery. So automated design, so what are the requirement, construction, end of the life phase emissions are there. Other than that, after that, generate agile inventory data. Inventory is the how inventory is the stock of the material which you have, either it's product or raw material, it's up to you. So from this, for the life cycle, how much time it will take to consume the product or consume the raw material, how much time to sell out the products. So from that, it will be useful to go for the automated simulation, which require the biofuel products and utility, how much utility depends operation phase emissions are there. and combinedly it will be used for the agile life cycle inventory and cash flow kind of processes. This is kind of process which will be generally used for the life cycle assessment. Then at the end characterize life cycle sustainability, how this LCA which you perform LCA study, which is how much sustainable for the futures. So for this you have to go for the discounted cash flow, the economics you need to add, and environmental impacts you have to understand. So this is the main goal of life cycle assessment. So what is the environmental impact of your process, of your product or of your technology, and how much economics it will be taken, it will economics it will be there for getting out this process. So that will be give you the automated impact and cost analysis, which is the final answer of LCNT. So the techno-economic assessment and uh, life cycle assessment combined together will give you the final process, automated impact and cost analysis out of it. Now, this life cycle assessment, as we you can see the resource extraction, material processing, and then product manufacturing, and what is the use of product and end life of product. You all thing needs to be understood in this. But this product manufacturing is the much more important, as our process engineer will be much more in detail will be there. So where we have to processes convert into sub processes and engineering software we have to use, then which are the sequencer of process changes and required, and they convert into sub process and sub process one to end, and how this will be operated by using which kind of model resources, which kind of technical constraints are there. Now our software you need to use, like mostly people are in the industry, people are used for the this is a process simulation software in the first end, and then it will eventually convert into the industrial mode of DCS or SCADA system. So first we will use this all this in the under the software of, let's say, SPEN or simulation software, different other simulation software. Then after this process engineering converted, and you will go for the life cycle thinking software. Then with the aspect, economic aspect, social aspect, this multi-objective optimization will take place, and iterative by iterative correction. Then you will get the decision making. So this feedstock deconstruction and biofuels and bioproducts input, feedstocks and conversion process data will be going to the lead. For that one, lead is like for the techno-economic analysis, life cycle assessment, system dynamics and filters, and it will eventually you will get the output, biofuel selling, price, and carbon efficiency. So how will we find the price? By taking care of each and every step and factors. Now, in the input of lead, you will get the capital cost, operating cost, and impulse and inventory. So, for suppose example, but capital cost are the purchase cost, installation cost, engineering, and construction cost, and finance. Operating costs are a feedstock, raw material, energy. Every time you have to use this one. And then emission inventory is upstream logistics and conversion process. So with this chapter is end, and this is the end of our whole this course. Also, next week we will discuss about the week 12 assignment problem, and then we'll summarize the all 12-week content very briefly, very rapidly, and that's it. That will be the plan for the next week. So at the end, I'm just quoting Marie Curie. She said once that nothing in life is to be feared; it is only to be understood. Now is the time to understand more, so that we may fear less. So like this, if you understand the thing, then you will don't have the fear of that thing. Like for the sake of exam, also you understand the whole subject very properly, then you don't have fear to be exam. And then you, if you have any doubt, you can reach out to me on this mail ID. And thank you for attending this lecture. I'm stop presenting. So with this, I conclude the today's discussion of the Biomass conversion biorefinery course. Week 11 discussion of the assignment problem, and week 12 discussion. And whosoever is taking exam of these courses, which I wish them all the very best. Give your best, and this is the very good subject to understand the biomass conversion biorefinery, which will be helpful for you if you have any further interest to go into research and other parts for this subject. So with this, I am leaving this meeting right now as no one is there. So good night and goodbye, and all the very best for exam. We'll meet next last time in the next Tuesday.